Hello, and welcome back. Today, we'll be continuing with the final part of the contact detector pipeline, which is the narrow phase. Now, if you recall, we have successfully determined whether or not we have potential collisions from the broad and mid phase. Now, here in the narrow phase, we are interested in doing two things. We want to do an overlap test to confirm whether or not there is actual overlap. And we also want to generate a structure that will be sent to the contact resolver. Now, there's going to be more things inside of this structure eventually, but for our purposes here in the error phase, if we detect an overlap, we want to go ahead and calculate a collision normal, a collision point P, and a collision depth D. Okay, so let's jump right into it. I'm not going to draw out the collision tree. I think we've seen it plenty of times, but as always, let's go ahead and start with the sphere problem. So we have two spheres, each with their own center and each with their own radius. So if you remember, as I just said, we were trying to get a contact normal, we were trying to get a collision point P, and we were trying to get a collision depth D. Well, for the normal, we always want it to be, and this is arbitrary, but it seems that standard practice is you always want to go from body one towards body two. And so that's actually pretty simple. That would just be taking the two center points, finding the direction between the two of them. So from C1 to C2, divided by the magnitude of that vector. And that'll very simply get us the collision normal. Now for the penetration point, we want to place it in the center of the two surface points. So here, it's going to look like it's in the center of the two spheres, but it's not. What we do is we follow C1 along the normal until we reach its radius point, and we'll go ahead and call that surface point 1. And then here, we'll do the same thing against the normal. We'll call that surface point 2. And then right here in the center, this is our contact point P. And so in order to get S, so S1, it goes in the direction of the normal. So it'll just be the contact normal times R. Well, yeah, that's fine. Technically, that might mean something else, but for our purposes, that's fine. And then S2 is in the inverse of the contact normal. And they're each using their own respective R's. So when we have S1 and S2, we can go ahead and just say that P is S1 plus S2 times 1/2. Now for the penetration depth, I want to actually look at this geometrically. So first and foremost, I actually forgot this, but our overlap function, we can say that there is overlap when the distance between the two center points squared is less than or equal to the squared sum of the radii. And now we can think about this geometrically by putting our 2 points that we have C1 and C2. And C1 and C2 make a line segment along the vector n. And a lot of you might know where I'm already going with this, but if we go ahead and place the radius, or the radii, onto this line segment, we see that R2 crosses R1. And it's inside of this cross here that is our penetration depth D. Now, eventually what we're going to want to do in the contact resolver is we're actually going to want to say that when we evaluate the expression, the distance between the 2 points squared minus the sum of the radii squared, we're going to want it to be equal to 0. But because we know that we've entered violation territory, D may be equal to 0, but it's going to be variable. So for the time being, we just solve for D by plugging in that equation, and we say D is simply C2 minus C1 squared minus R2 plus R1 squared. And this will actually be the basis for almost all of the overlap functions coming up. Okay, so now let's go ahead and move on to spheres versus capsules. And we're not really going to be doing anything different, but instead of 1 point, like we have with the sphere, we have 2 points on our capsule. So the capsule is an inner line segment defined by 2 points and some radius r. I'm going to call this S1 and S2. So the best way to solve this is, let's go ahead and get rid of radius for now. And we are going to look at this. Here, we are simply trying to see what is the closest point from this point onto the line segment. And then we'll go ahead and call this SC, or, well, actually, no, because SC is going to be the sphere center. So we'll just call this L, like Dirk did. So L. So now that we have that point, we can bring the radius back in. Let's go ahead and drop this down. So we have C, and we have L. So now if we go ahead and put in the sphere's radius, and if we put back in the capsule's radius, we're back to our sphere-sphere problem. And it turns out that we can compute the normal, the contact points, and the penetration depth in exactly the same way. All right, and now moving on to spheres versus hulls. As you might guess it, the problem is incredibly similar. So start with our sphere, as we do. And then let's go ahead and represent our hull with our box. So I've gone over the convex hulls before. For the purposes of collision detection, and specifically overlap, we can reduce it to its vertex set and just look at the vertices for now. Kind of similar to what we did with the capsule segment. We also go ahead and get rid of the radius for the sphere. Now we're left with these points. And what we're going to do is similar to the capsule. We want to find the closest point on the hull from the sphere. And in order to do that, we're going to take this and these, and we're going to plug these into an algorithm called GJK. And what that's going to do is it's going to give you back a simplex that represents the configuration space obstacle. And when I go into the video about GJK and in depth, I'll talk more about this. But for our purposes, all you need to know is that if you take the barycentric coordinates of the vertices on the simplex and then multiply those weights by the contributing vertices of the shapes. So in this point, the sphere will always be the vertex that is contributing in the simplex for one object. However, any of these points might be the contributing vertex in the simplex. So when you take the barycentric coordinate of it and multiply it by the original vertex, you get back the world space position of it. And then when you take all the points and all the weights, you get back the actual point on the object that is the closest point. I probably butchered that explanation, but again, when I go into GJK more in depth, I'll make sure to cover it thoroughly. But for all our purposes, all we need to know is that this essentially gives us back that closest point L. And we don't have a radius like we did with the spheres. So instead of the overlap checking the distance between 2 points and the square, the square of the sum of the radii, we just simply say it is the distance between that point L and the capsule center squared is less than or equal to the sphere's radius squared. And the reason why this works is because when we make our contact point P, we just set that equal to L in this case. And then N will simply be L minus SC divided by the magnitude of L minus SC. And then D simply just becomes setting this to 0 and then solving for D as the error. So I had to restate something. What I was just saying about GJK with convex hulls and the spheres only works if you're in what's called a shallow penetration. So if we're in a case like this where the center of the sphere is outside the hull, we can use GJK for this. If we're in a configuration where it's something like this, where the center of the sphere is inside the hull, we're in what's known as a deep contact or a deep penetration. And we would need to do the separating axis test. And in that case, what's going to happen is N will just be the minimum translation vector. That's what I think it's called. D will be reported from the separating axis test, and then P, I believe, I'll get back to you on that in the code. I do apologize about that. I did forget about the SAT or deep contacts. But moving on, sorry about that. We can enter into the world of capsules now. And we're going to look at capsules versus capsules. So, as we saw before, a capsule is an inner segment with a radius. And we've kind of already solved this problem once. If you remember, with the spheres, we took away the radius from the sphere and the capsule, and we computed on the line segment of the capsule the closest point to the sphere. So we're kind of going to use that same idea. We're now for point 1, or for segment 1, we're going to find on segment 1 the closest point to segment 2. And very clearly that's right here. So we're going to call this S1. And then on segment 2, we want to find the closest point to segment 1, which would be right here. And then now that we have our points, S1 and S2, we can simply add back in our radius and do the same sphere versus sphere that we did last time. And the same overlap, except instead of saying it's the sphere centers, it's these virtual centers. Although capsules afford us an interesting opportunity, and it's our first look at being able to generate 2 contact points. So let's go ahead and say we end up in a situation like this, where we'd like to be able to stack capsule 2 on capsule 1. Well, if we're in a situation like this, we can detect that these 2 segments are parallel, and if we detect that they're parallel, we essentially go into a separate branch where we're no longer doing that closest points on the segments. We're going to be generating 2 virtual spheres and solving, or sorry, 4 virtual spheres and solving for 2 contact points. And the way we would do that is we take the side planes of capsule 1 and you're going to clip the inner segment of capsule 2. And then this is kind of where Dirk lost me, because he says you keep the points whose distance is less than the sum of the square of the radii, what I believe he exactly said. I have thought about that, and I have continued to think about that. The best I can come up with is he's saying just keep the clipping points. If assuming that's what he's saying, and I mean in my code that's what I do, and I'm able to stack capsules relatively stably. After, if that's what it is, after we get the contact points, we go ahead and, like with the spheres, go ahead and generate surface points, and then we put the 2 contact points in the middle of those surface points. And that's how we can go ahead and do capsule stacking. And again, the normal, the collision point and the penetration depth are all solved in the same way using the virtual sphere on the 2 points. Okay, so this is where the rubber really starts to meet the road, and we move on to capsules versus hulls. So just like with the spheres, there's going to be a deep and a shallow case. In the shallow case, what we're doing, well, we always assume, just like same with spheres, I know I kind of didn't say this, but we always assume we're in the shallow case. So we attempt GJK. If GJK fails, we assume we're in a deep contact. If GJK succeeds and the distance is less than the sum of the radii, we are in a shallow contact. Same holds for spheres as with capsules. Apologize, that was blinding. So, and this will be a separating axis test, just like with capsules. Or sorry, spheres. Oh my goodness. So again, I'm not going to be really going into GJK and SAT just know that these are two tests. I will eventually, just not right now, but these are two tests that return you either the collision information itself or variables that can be used in conjunction with existing information to compute your collision data. So let's go ahead and first assume we are in a shallow contact. So just like with the sphere and hull, we're going to be sending two sets of contact points into GJK. And then from GJK, we're going to get back that CSO simplex. And then this all really boils down to getting the closest point on the hull, getting the closest point on the segment. And if you remember, again, I really feel like I butchered that explanation. But if you take the barycentric coordinates of the simplex and multiply those weights by the contributing vertices from the original object, that'll give you C and L. And then once we have C and L, we can move this into the whole sphere problem, which we've already solved. And that'll take care of your shallow. For a deep penetration, that's essentially one in which, so just like where the hull contains the sphere center for a deep sphere contact, this is when the hull contains part of, or the whole or capsule segment. And in this case, what we're going to do is we're going to send these two objects to the separating axis test, and that's going to give us back that normal, which is equal to the minimum translation vector. And basically what that's going to be is, in this case, you can see we kind of want to push this capsule out this way. So the normal will either come from a face of the hull or the cross product of two hull edges. But again, we'll get into that. For now, just trust the black box of magic that this stuff works. Then P will be the closest point on the hull, and oh my gosh, wow, I'm gonna have to brush up on the SAT before I make the video about it, apparently, because I am drawing blanks here. I really apologize for that. Feel like I'm robbing you. And then D again is reported by SAT. There is a case where we can stack the capsule on top of the hull. Dirk did talk about that. However, I have not really been able to figure out an elegant solution to work that in. So if I can figure that out in the near future, I'll make a follow-up or an addendum, or maybe even the code video if I can figure it out by then. I'll show you how to do it. But unfortunately, for the time being, a capsule even resting on its side, perpendicular to a face on a hull will only generate one contact point. But the good news is I haven't really seen too many issues with that, though it does teeter a bit. Alrighty, so let's get on to the last non-mesh contact. We'll still talk about those. We are now dealing with two contacting hulls. And basically, our overlap condition is going to be that the separating axis test returns an empty set, and we can't find a separating axis. So let's go ahead and say we do find a separating axis. And this is going to be a very quick explanation because I'm just not going to go into SAT right now. But unlike Capsule and spheres, I can actually talk about this one. So let's say we do get we detect with SAT. We can either have detected a face contact or an edge contact. In the case of a face contact, the normal is simply going to be the normal of the reference face. So if you think about it, the holes are the faces are all polygons, and so you can calculate the surface normal of that polygon, and that will be the collision normal. The collision points are gotten by taking the incident. So let's say this is the reference hole, and this is the incident hole, and we're going to say that it's this is the reference face. This would probably be the incident face. So what we're going to do is we're going to take the points of the incident face and project them on to the plane of the reference face. And then we're going to use the side planes of the reference face and then clip these points. So essentially, you get something like this, and you lock in the collision points. And then you move the points onto the face. So your collision points P are basically going to be the projected incident points plus clipping. And then D, and for each of these points, D and N will be the same. D is going to be reported by SAT. Now for edges, we're only going to have one contact point. The normal of that collision is going to be the cross product of edge 1 and edge 2. The collision point, if you remember how we were able to find the closest points on the two edges to one another for the capsules, we end up reusing that, and we say that it is the closest points from edge 1, edge 2, and we put it in the center of those, so multiply that by 1/2, and D, as always, is just reported. But that covers the theory. Obviously, in the next video, we'll be going over the implementation of all of these. But now let's go ahead and talk about mesh collisions, because we've kind of already solved it, except there's some special things to take into account. So for mesh contacts, the trick is to realize that we've kind of already solved these, and that the triangles in your mesh are really just flat holes. So we're not going to be reusing the actual hull versus sphere or capsule or whatever test, but we're going to be using the idea of it, where we're trying to find a disjoint point with the radius to a solid point. and that'll work for the sphere and capsule methods. Hall mesh is a little, I ended up going a little different. We'll talk about that, but for now, Dirk ended up talking about a wonderful paper by Pierre Terdyman that I ended up using essentially to write the algorithm for spheres and then extending it to the algorithm for capsule and mesh collisions. So for sphere versus mesh, we start with a sphere and then a set of triangles. And then for each triangle, we want to find the closest point from the sphere to the triangle. And we do this using the barycentric coordinates. And the reason we do this is that if the closest point returned by this, we're going to call it L. As we checked before, if L minus SC squared is less than R squared, then we have overlap. And the reason why we want these coordinates is that if we detect this, we want to go then say if we have a phase contact, basically meaning that u, v, and w are all greater than 0, we want to go ahead and cache the triangle vertices and then create a contact point. And this will be, the contact point will be created in the same way as the sphere in Hall, where we put the contact point as the closest point L. The penetration is the distance from the surface point to the closest point, and then the collision normal would, in this case, be the face normal. If we don't have a face contact, we just delay the triangle for further processing. And that takes care of the first loop. So on the second pass, we go through all the delayed, and then we see, for each delayed, we go ahead and we're going to cache. We're going to cache the vertices of the delayed contact. And the reason for that is if we check a triangle that shares a vertex or an edge, and we have already created a contact that includes that vertex or edge, we don't want to create another contact, especially for spheres because there's only one contact point. But so let's say we're delaying. We go ahead and update the cache regardless now, and we get back that old point L, and we essentially use L, or I call it L minus C becomes the contact normal. And there's a fallback that if this is undefined, we just use the surface normal. But basically that's it. You just go through each triangle, try to make a face contact. If you can't make a face contact, you just delay it and then create either an edge or vertex contact. And the main difference is if it's a face, always use the surface normal as the contact normal. If it's not, try to use the direction between the closest point and the sphere. And if that fails, just fall back to the surface normal. So for capsules, it's actually almost identical. At least what I do is I essentially run that loop twice, once for each segment point. Hey there, I was watching this section back during editing, and I wanted to correct what I was saying. What I drew versus what I said seemed to be different things, and I felt it could be very misleading. So, in order to actually convey what I was trying to say, was that for capsule versus mesh collisions, we're essentially going to do the same sphere versus mesh collision as just talked about. However, we do it once for each segment point. What I failed to really articulate was that the vertex cache is going to be shared between each test, and it's only the delayed contacts which are reset. And that little gap that you see, what I'm talking about is the section is picked up due to how the radius is checked from the barycentric coordinates. Which leaves us with one final pain in the ass, which is whole mesh collisions. Now, I'm going to spare you the details of everything I tried and tested, and I could just not get individual triangle meshes or individual triangles to robustly collide with hulls. So I use an algorithm. It's not really a name for it. It's a convex decomposition algorithm, and I essentially turn it into I turn it from a hull mesh problem into a complete hull versus partial hull problem. Basically, imagine if you took a cube and then stripped off 3 of the 6 faces. Well, we still have a partial hull that all of the math of SAT works on, minus the edges. You have to handle those a little different. But more or less, for each of the complete faces that exist, we can still do SAT. So the idea is, in your triangle mesh, get the minimum set of triangles, take those, move them into, or take your triangles and run them through the decomposition algorithm and get back a partial hull. Use a specialized separating axis test that takes in the partial hull and the complete hull, and then basically this is actually almost identical to the hull versus hull problem, except we want to always not always, but we want to heavily bias the partial hull as being the reference face instead of trying to just pick one or the other. We always want to make sure that the partial hull is heavily biased and everything seems to be stable. Using this, I was able to throw a box all across the terrain and never got stuck and never, that wire mesh issue. None of those problems. It just simply, to quote Todd Howard, it just worked. But thank you all. I really appreciate your time. If I know this was a whirlwind tour of collision detection, I'm pretty sure if you watch Dirk's video and this, Dirk really goes over everything. I just wanted to add kind of a pictorial geometric kind of visual aid. But in the next one, I will be going over the actual implementation of the narrow phase test. And then after that, we can get into the GJK SAT and finally move on to what is probably not the hardest, but the most fun, the contact resolver. So thank you, and I will see you in the next one.